let me share my screen and get the presentation up here. Okay, can everyone see the presentation?
Yes, we can.
All right, great. Okay. Well, thank you for having me. My name is Greg. My call sign is WA1JXR. And I'm going to be giving this presentation at the ARRL New England Ham Expo coming up. So I was asked if I could do a precursor, and I said certainly I could. That would be a great dry run for me anyway. So here we go. So what I thought I would do is end-fed half-wave antennas seem to be very popular now with portable applications and QRP and all of that. So what I did here is I kind of used that as the vehicle for explaining how the EZ-NEC antenna modeling software works.
Greg, oh, go ahead. I'm sorry, go ahead.
So like I said, for portable operation, the end-fed half-wave is great. It solves a lot of problems. You can easily throw a wire up in a tree or with a single, fiberglass or push-up pole, and then all you need is the 49-to-1 matching transformer at the end. The center-fed dipole are great antennas, but you have that feed line in the middle, and you have a longer feed line here. You can put the feeding transformer at the end right near where your setup is and have a very short feed line. The other advantage is the center-fed dipole is really a single band antenna, where the end-fed antenna not only works on the fundamental half wavelength that it's tuned for, but on multiple harmonics of that. So you end up with a multi-band antenna. But the patterns of the two antennas are pretty much identical. It's a half-wave dipole, and as you'll see coming up, the patterns will be pretty much what you would expect from a half-wave dipole. So if we start out with half-wave resonant antenna, depending on what band we want to start with, whether it's 80, 40, or 20, then that determines whether it's 135 feet or 33 feet. But you see all the various harmonic bands that the antenna will then operate at. And so once again, it's still just a half-wave wire antenna, but just fed at the end versus being fed at the middle. The difference being one thing that makes the center-fed dipole so popular is the impedance at the center point of a dipole is in the 50 to 70 ohm range. It varies with height above ground, but that makes it a instant, impedance match to 50 ohm coax. You hook the coax up at the center and boom, there you go. You don't need to do anything else. Where at the very end of the half-wave wire, the impedance is very high in the 2,500, 3,000, even up to 5,000 ohms. So you have to do some matching network when you end feed the half-wave dipole. So here, if we have an 80-meter dipole and we look at the fundamental frequency, here's what the voltage and current distribution look like over the dipole wire. You see the current in blue and the voltage in green. And if you look at that red line in the very middle, you see that we all remember that impedance is the voltage divided by the current. So you have a small number for the voltage and a large number for the current. So you end up with a small impedance at the center. If you go over to the red marker at the 60% point, that would be the 1/3, 2/3 division of the half-wave wire. That's where you would feed an off-center fed dipole, an OCFD. And the impedance at that point is in the 200 to 300 ohm range. And if you continue all the way out to the end of the wire where the zero is there and that red line is, you see that you have a very high voltage, the green trace, and a very low current. So when you do the voltage divided by the current, you get a large number out there at the end. So now we're looking at the voltage and current distribution, but now at the second harmonic at 40 meters. And so now instead of, just the one wavelength blip, you see the two blips of the blue and the multiple blips of the green, the voltage and current. But once again, if you go back now and look at the very end of the wire, you see that the spot at which the green and the blue are with the high voltage and very low current, it's exactly the same as it was at the fundamental. So once again, now at the second harmonic, the impedance at the end is exactly the same. And for the third harmonic, you see the same relationship at the end of the half-wave wire for the voltage and the current. That's why this antenna can operate over multiple bands, because of that repetitive nature of the voltage and the current. Here we see an expanded scale, but with now at 20 meters. Once again, the same voltage and current ratios out there at the end. 15 meters, likewise, and 10 meters, the same. So that's how this antenna is able to operate on all those other frequencies, is because it just so happens at the end of the wire, the ratio of the voltage to current, i.e. the impedance, is the same, and we can use the same matching network, the same transformer, to match it to 50 ohm coax. Okay, so that was a little overview of the end-fed half wave and kind of how it works. Now let's talk about the antenna modeling. What is antenna modeling? Antenna modeling is a computer simulation of antenna performance. The computer simulation allows the antenna performance to be analyzed and parameters changed to see how they affect antenna performance. What are some of the parameters we can look at or change within the model? Well, of course, antenna gain, things like front to back ratio, beam width, takeoff angle is often very important. If you want a long distance antenna, you want a very low takeoff angle. And of course, the impedance at the feed point, the complex impedance, the SWR, and then all the various plots of the antenna pattern. There's a far field plot. You can get a three-dimensional plot, what they call an azimuth plot, and that's kind of like your north, south, east, west plot of the where the energy is going. And then the elevation plot, that's kind of the takeoff angle, what angle from perpendicular to the ground is the energy leaving the antenna site. Any questions so far? Please, if as I'm going along, if there's something you don't understand, by all means. And let me just take a minute. I forgot at the beginning to tell you a little bit about myself, but I first licensed as WA1JXR in 1967 and upgraded to general a year later. Back then, novice licenses were only good for a year, so you had to upgrade your license within a year. As a 14-year-old, shuffled off to 1600 Custom House in Boston and took my general test and passed it, and then later got my extra class. Ham radio greatly influenced my career, the interest in electronics. I took electronics in high school. I went to a VOTEC high school my last few years. high school. And from there, I went on to, they called them junior colleges back then, not community college, Rhode Island Junior College, and got an associate's degree in electronics technology, they called it. And then I transferred to the University of Rhode Island after that and got a bachelor's and master's degree in electrical engineering. When I graduated, I moved up originally from Rhode Island area, Westerly, Rhode Island, little town in the southwest corner down by the ocean. I moved up here into the Central Mass area because I got a job and started working with Raytheon Company. And I worked for Raytheon Company for 42 years, working on radar system as a senior principal RF microwave design engineer, and retired at the end of 2019, just before COVID hit. And now enjoying my retirement. I can play radio, and my other hobby is bluegrass music. So I can play music and play radio now almost full time. Okay. So here's what the some of the plots look like. You see the three-dimensional plot at the top. The azimuth plot is, like I say, kind of looking top down at the antenna, and it gives you the north, south, east, west. And then the elevation plot, if you were to take a knife and do a vertical slice through that three-dimensional plot, that gives you the elevations plot, and that shows you what angle the energy is leaving the antenna, versus the ground. You can also take a look at impedance and look at the SWR of the antenna with the antenna modeling software. I'll show you that. So some of the parameters that we can control in the model is, of course, the physical layout of the antenna. So you have to tell the model and tell the software what kind of antenna. So you have to describe that antenna in the model, whether it's a dipole, a Yagi, or a quad, or vertical, or what it might be. Of course, frequency, height above ground, what type of conductor you're using, what type of ground the antenna is sitting over, how you have the transmitter and or the feed line hooked up, and then any other loads or traps or transmission lines. You can model all that stuff. So if we take our end-fed half-wave antenna, you see a picture, kind of a picture of it here with the half-wave wire. Oops, I took this from a center-fed dipole, and I forgot to fix the gap in the center of the wire where the center-fed was. So, but that wire is supposed to go out, all the way. And so you have the matching transformer at the end, and of course your feed line. And as we might all remember, if you ever wondered where that half-wave dipole length formula came from, well, the wavelength of a wave is given by the speed of light divided by its frequency. And so 300 million meters per second divided by the frequency in cycles per second. And if you do that, and instead of calculating it in metric, you convert it over to feet and all that stuff, you end up with 492 divided by the frequency in megahertz. But the radio wave does not travel at the speed of light in the wire. The wire actually slows it down a little bit. So there's a K factor in there, and for wire, a number of 0.95 is often used. So if you take that 492 and you multiply it by the 0.95, that's where that familiar formula, which we've probably all seen before, 468 divided by the frequency in megahertz, that's where you get the half wavelength calculation for a wire antenna. Like I said, the half wave dipole is a resonant antenna, but the feed point impedance, like I said, at the end is, between 2,000 and 3,000 ohms. So we need to divide that impedance down by a factor of like 49, 50 to 1 in order to get it down near 50 ohms where it'll be a good match for the 50 ohm coax. So when we model the antenna, we can model this antenna as just a single wire. In the antenna model, they ask you to specify how many segments you want to break the wire up into. And this is just how the antenna modeling software engine works. It's called the NEC, method of moments calculation. NEC stands for Numeric Electromagnetic Code. It was developed by Lawrence Livermore Labs way back when. They used to have big mainframe computers to run it, but of course now we can all run it on our home PC or probably even on the phone. The NEC guideline is you want at least 10 segments per half wavelength. So you'd want to have at least 10 segments for this half wavelength wire, but you can often use, more segments. You get a little bit better resolution. You don't have to go crazy, but you could easily have, 25, 30 segments. Insulators are not required in the model. It can be modeled as a single wire, and because we're feeding it at the end, we'll place the source at the very end of the wire. So like I said, you have to describe to the antenna modeling software where this antenna is in space. And so we use the common, what they call Cartesian coordinates in mathematics, XYZ coordinate system here. And we have to just then tell the software what the X, Y, and Z values are for each end of the wire, end number 1 and end number 2. And then it knows where the wire is in space. So let's talk a little bit about antenna gain. That's something that we're often interested in with antenna, because we'd like to have an antenna that has some gain to it to increase our signal. And so there's a thing in antennas and mathematics, actually, that's known as what's called an isotropic source or an isotropic radiator. And what that is that's like a pinpoint source where energy emanates in all directions like a sphere going out from that source. There's no real such thing that exists in the real world, but there are things that approximate a isotropic radiator. So think of it as if you have a lamp and you take the shade and you just have the light bulb, right? Well, that can kind of be thought of as an isotropic source. Or if you had a old-fashioned flashlight, because they're all LED now, but the old-fashioned flashlight that had the little bulb in the end, if you take that apart and you just have the little bulb sticking up, right, that emanates light in all directions, that could be considered like an isotropic source. So as with all things, conservation of energy applies, and your antenna is a passive device, meaning you're not feeding additional power to the antenna like you would an amplifier or something like that. So the antenna doesn't create more energy. So how do we get this concept of antenna gain then? So antenna gain is really just directing all the power that is available from the isotropic radiator into a particular direction. So take, for example, the flashlight. You have that, if you take it all apart, you have that little bulb, right? It's not very bright because the energy is going out in all directions. You now take that little bulb and you put it into the, components at the end of the flashlight. You put it into the reflector and you put the lens on the front. Now, all of a sudden, you have a much brighter beam. Well, there's no more energy being provided by the light. The gain is you've taken all that energy that was going in all directions and you've redirected it to a particular direction. And that's where the concept of antenna gain comes from.
Okay, makes sense.
Is there a question? Okay. If the gain is referenced to, you can reference the gain to an isotropic radiator.
You just muted yourself, Greg.
I'm sorry. Yeah, I saw that the host muted. Let me go back. If the gain is referenced to an isotropic radiator, it's dBi. If the gain is referenced to a dipole, it's often shown as dBd, D for dipole. And the gain of an isotropic radiator in free space, the gain of a dipole reference to an isotropic radiator, I should say, is 2.15 dBi. So the antenna modeling software that we're going to be talking about today is called EZ-NEC. And it was developed by ham radio operator Roy Llewellyn, W7NEL. Roy was a professional antenna engineer as well as a circuit designer. He had I think he worked for Tektronix for a while and then got into this modeling software stuff, but he developed this software and it was actually available, professionally for like professional broadcast stations and all that kind of stuff. But he did have, lower cost and versions that were available for like hams to use. But he has since retired and he's offering his Pro Plus version 7 free on his website, www.eznec.com. You can go there and download the software for free. And that software used to cost, back in the day, many hundreds of dollars to get the license to use it. So that's a very gracious thing that Roy is doing for us. And the Pro Plus version allows you to use up to 45,000 segments. So you can see that you can design some fairly elaborate antenna systems because you have a lot of segments there to work with. And the nice thing about EZ-NEC is when you download it, there's a whole library of models that come with it. So it's not like you get this software and you got to figure out, okay, now where do I even start? You can go to the library, you can find a simple model like a dipole, load it in, and you can immediately start using the software without having to actually create the model from scratch. So here's what when you bring up the screen, here's what the EZNEC screen looks for. You've got some action buttons on the very left, some selection buttons kind of next to the window, and then the usual kind of menu things at the very top. And then in the information window, you see all the pertinent information about the antenna model and how you manipulate things. So I'm going to stop share at this point, and I'm going to share. Let's see, I gotta open up the model. There we go. And share my screen. Okay. Let me hold on a minute. Let me stop sharing. Let me close. There we go. That's a little better. Well, so now we try that again. Okay. So now you see in the very middle of my screen, that's the EZ-NEC window. Unfortunately, it doesn't get any bigger than that. There's no way I can make it larger, so you'll have to bear with me. So what I've done here is I've gone in and I created a model of a half-wave antenna. And so by show you that, let me go and click this button over here on the left that says View Antenna. And you'll see the three-dimensional coordinates come up, and I can grab this with my mouse and I can move it, and you can see the green line there is the wire, and I've placed that wire on the along the y-axis, starting from the origin and going out, and I've placed it some height z high and some distance y long from, here is 0, y equals 0, and then out here is the final length. I've also added a small piece of wire going down at a right angle, wire number 2 there. You'll see the little green tail, and that's in order to get the model to work, you need some sort of a counterpoise in order to get a half-wave antenna to work. In the real world, when you hook up your coax to the feed transformer, the shield of the coax kind of acts as that counterpoise. Some of the half-wave antennas that you can buy, they actually give you an extra lug on the matching box where you can hook up a piece of counterpoise wire and let it hang down as well. But anyways, so here's what I have for the model. Any questions regarding that? Everybody understand what we're looking at here? All right, let me close that out. And if I open up this table here, this is the wires table. In tabular form, exactly what I showed you there in the picture. You have 2 rows here, wire number 1 with N1 and N2, and I've put in the XYZ coordinates for those ends. So my wire is 135 feet long. You see Y at N2 is 135 feet. And Z for the wire is 40 feet. So this is a 135-foot wire, 40 feet above the ground. The second wire, you see, I've put that little wire hanging down that's 6 feet long, going down vertically from N number 1. I forgot to mention with the view antenna, this red circle here, that's the source. So that's where you would attach the feed line. For the model, what I'm doing is I'm just putting a source there. So it's providing RF energy into the wire, just like the feed line would do. And in fact, there's another table where you go in and you specify where you want that source. And here I'm saying I want it in wire 1 and I want it located 0% from N1, so it's right at the end. The other things that I've done here is I've put it over what's called real ground, so it just approximates, average ground conditions. If you happen to know where exactly what the conductivity of the Earth is where you are, you can put those numbers in if you happen to know them. You can also have no ground, and so model it in what's called free space, or you can also model it in what's called ideal ground, perfect ground, which of course none of us have. We'd love to have that, but the model allows you to do that. Wire loss, you specify what kind of wire. Here I'm specifying copper. I want my units to be in feet. The default plot that I want to come up is 3D. And you see here alternate SWR Z sub 0, alternate impedance. I've put in 2450 ohms, which happens to be 49 times 50. So that's how I'm going to show you what that 49-to-1 transformer at the end does, and what the impedance that the 50 ohm coax will see by using this alternate Z sub 0 term. Okay, so now I can go and we're ready to have the software do its magic, and I can click this far field plot and it'll go through and calculate, and there you see that's what the three-dimensional plot of the antenna looks like. I can grab that with my cursor and you can see it there. The wire is going down horizontally here, and the antenna pattern maximums are broadside to the wire, but that's probably the classic, figure 8 pattern that we've often seen with dipole antennas. If I go over here and I click azimuth plot, now we're taking, if you were to take a knife and cut through this three-dimensional plot horizontally, you'll see a two-dimensional plot, and so you see the common figure 8 pattern that you see from a dipole. Over on the left here, it's showing the gain of the antenna here at the outer ring. The maximum is 7.13 dBi. So that's pretty much what you get from a half-wave dipole. 6.5 to 7 and change dBi is what you would normally get. Now remember, I said the half-wave dipole is 2.1 dB above the isotropic radiator, at 2.15 dBi, but that's a half-wave dipole in free space. The reflections from the ground, that RF energy that hits the ground gets re-reflected up and contributes to the additional gain of the dipole. So that's why this antenna has 7 dBi of gain versus just the 2.15 of the dipole in free space if there's no ground reflections. I can also now click on this other plot here. And so here is the elevation plot. If you were to take that three-dimensional figure and take a knife and do a vertical slice through it, here is the plot that you would get. And so this is kind of like the angle at which the energy, so down here is the ground, and so you see the energy taking away from the ground, and we see that in fact the thing here, so I can see it. The takeoff angle is 55 degrees. So this is, a moderate antenna. And typically what you would get with a half-wave dipole, it's 40 feet above the ground. Let's see, I got to go back. Let me see I forgot what frequency. Okay, so we were looking at this on 7 megahertz on 40 meters. If I change the frequency to a different band, obviously the plots will be different. For example, if we go here and let's look at 80 meters, make that 3.5 and redo the plot, you see that the patterns look totally different on 80 meters. Now we no longer get that figure 8 effect, and you'll see that the azimuth plot on 80 meters, it's pretty much circular. It's omnidirectional, and most of the energy is going straight up. And you've probably heard the term NIVIS, nearly vertical incident skywave. Well, that's essentially what this, at 40 feet, an 80-meter dipole is pretty much a NIVIS antenna. All the energy is going straight up. Good for, local region work, but it's not going to get you, into Europe or you know, Japan on 80. Now, if we go and look at some of the, let's look at it on 15 meters, for example. See, the pattern has become a lot more what I call spiky. You got more of these lobes. But we've also gained some gain. We're up around 10.7 dBi of gain now. And that's because, you know, the wire that we're using, 135 feet, that's multiple half wavelengths on this frequency. So the more wire, the more gain you get. And if we take a look at the elevation plot, we see now that our elevation angle is nice and low. We're down at 15 degrees. So this would be a reasonable antenna on 15 meters for longer distance work. This takeoff angle and what the patterns look like all have to do with the height above ground, because it depends on how those reflections off the ground recombine with the energy coming off the antenna to make the ultimate pattern. All right, close that out. I can now, let's take a look at what the impedance looks like. And so I'm going to sweep this from 3 to 30 megahertz over the whole HF band. And we'll let that run and calculate. It'll take a minute or so. I asked it for 1/10 of a megahertz step, so it's doing a lot of number crunching. We're getting there. Okay, so here's what the SWR looks like. And that doesn't look very good, right? But if I go up, but that's in reference to 50 ohms. Just looking at that end of the wire as if we wanted it referenced to 50 ohms. Well, the 49-to-1 transformer actually allows us to look at it at, you know, 2,450 ohms. So if I go up here and I select that alternate impedance, this is what the 50 ohm coax is going to see when you screw it onto that 49-to-1 transformer. So you see much better performance here. So you see, you know, all of the resonances here. You see there's your 80 meter resonance, you know, your 40 meter resonance, 30 meters, 20 meters, 17, 15, 12 meters actually, and then 10 meters is way out to the end behind. I can't get to it with it because my Zoom screen is in the way. But you see, and you know, all the impedances are, you know, down 1.5 to 1 or so. So that's not bad. So you have a multi-band antenna with one wire. You can use it over multiple bands. You get reasonable gain that you get from a half-wave dipole. But now you have a multi-band antenna, very simple, just a matching transformer, a box at the end, and maybe a counterpoise wire sticking down if you need it. And you've got a great simple antenna that you can use on multiple bands and easy for, you know, portable use. Okay, let me stop my share. And go back to the presentation. Okay. All right. So anyways, that pretty much wraps up what I wanted to say. I hope this seminar on the NFED antenna has piqued your interest in maybe trying one. They're great for POTA, SOTA kind of stuff. Also, if you're interested in trying the EZNEC software, by all means, go to EZNEC.com and download your version for free. And then you can try modeling some of those antennas that you want to put up in the backyard or portable use and see which one will fit your needs. As you're going along and using the software, if you come up with any questions, by all means, do not hesitate and you get stuck and you don't know, you're confused and you don't know what to do, by all means, shoot me an email. My call sign at adolrl.net or comcast.net, either one will work. And I'll be glad to spend some time with you, even get on Zoom if we need to, and help you get the program working. So let me stop my share, and that's all I have to say. Any questions, comments, anything anyone would like to talk about?
I have a
Like-
question, Greg.
Yeah.
Let's see. Okay. I've been using the NFED for a while. I go camping. I have a 31-foot pole, and my antenna is roughly at 45 degrees. And I've always put the end where the coax is, where the transformer is down, maybe on the ground or near the ground.
Yeah.
Should I be doing it the other way around, putting it at higher up?
No, it doesn't matter. And it's more convenient to have it down near the ground because that way
Oh,
you
it's
have,
much
you
more
know,
convenient.
shorter feed line. So yeah, no, it doesn't matter. That's what I would do. Yep.
And what about the angle of the antenna?
I mean, you know, your pattern's probably going to change a little bit from the ideal things that I'm showing you here, but in all reality, it's not going to make a lot of difference. You know, obviously, you know, the higher the better, the higher up you can get it, the better. But you know, when you're dealing with, you know, POTA, SOTA, and you have to kind of deal with what you have or the push-up pole you have. So yeah, just use what you have, and I'm sure it'll be fine.
Cool. Thank you. Great presentation.
Oh, thanks.
We do have a question over here, Greg. I'm just walking a microphone over.
Hey, Greg, just had a quick question. Now, obviously, you used EZNEC as an option. Have you had any experience using like ANA or anything like that? And what's, you know, why that one versus another one? Or is it just kind of what's available? And
Yeah, I'm sorry. When you asked your question and you said the name, you dropped out.
oh,
You
it was
said-
a ANA?
Oh yeah, Mama Gal or whatever they call it.
Correct, yeah.
Yeah. It just enough. I mean, I believe they use the same NEC2 engines, both software packages. I've used some of those other programs. I personally find Roy's EZNEC software a lot easier to use. I think it's a lot more human friendly, you know, the human interface and everything. With some of those other programs, I found it a lot more. I mean, if you're a computer guy, you know, and you like, you know, creating, you know, numeric files, because some of those things you have to like load in these, you know, numeric files and so forth. I don't know. I mean, it's sort of, you know, whatever you're used to, but they're pretty much use the same, you know, calculating engines. So if you're used to one and you like it, then it's fine. I started with EZNEC and I just find it very easy to use.
Thank you.
And it has a lot of tools. The help file that Roy created that comes with the software, I mean, it's like a complete, you know, tutorial manual. You go in there and it'll show you everything. And he's created I mean, I've only just shown you, you know, the very top scratch of what all the options that are available in the tool.
Greg, I have a question.
Yeah.
This is Jack, WM0G. If Can you work this with an H-plane antenna or just antennas that are in the E-plane?
I think you can work it with either. I've never tried, but I don't see why you couldn't.
Okay, because being 90 degrees out of phase with
Yeah,
the E-planes.
Yeah, I don't think so. I mean, as long as you can describe the antenna to the model, it's going to show you what the electromagnetic wave is. And of course, you know, the electromagnetic wave is a composite of the E and H planes. So,
Right. Okay. Thank you.
yep.
Do we have any other questions for Greg? Does anyone online have any questions? I see a question from Jay. Go ahead, Jay. You're gonna have to unmute yourself. There you go.
Yeah, thanks. Antenna modeling is can get pretty complicated, and Greg, I think you did a great job of explaining how the model works in a way that people can understand it, and hopefully people will try to use it. I've used it quite a bit and made a lot of mistakes with it, but it's fun to create an antenna and then try to build it and see what the differences are.
Oh,
So,
absolutely.
but I think you
Yeah.
did a great job explaining the
Yeah,
the setup and how to
Yep.
use the model. Congrats.
Thanks. Thank you. Thank you for the kind words. I tried to keep it as simple as I could because you can really get, you know, but it's a great tool. I mean, you know, just by playing around with the software, you know, you create a model and then you kind of say, well, I wonder what would happen if I do this. So you go in and you know, bend the wire or change the height or whatever. And you learn so much about antennas by just, you know, playing around and doing all the what ifs, you know.
Yeah, and since antennas are among the few things that we can still build easily,
Right.
it's something I'm really interested in and have had a lot of fun with. So thanks
Right.
again. Great presentation.
Yeah. Well, yeah, I often, when I'm helping new hams, especially with wire antennas, I'm kind of old school, but I don't believe you should ever buy a wire antenna. You just go buy the wire, buy the insulators, and build it yourself. But you're right. It is one of the few things that, as hams, we can still homebrew, because we certainly can't homebrew our, you know, surface mount transceivers anymore. Even as an electrical engineer, I don't try that. All right.
Very good.
Anybody else?